So one of our goals before the end of the semester is to solve some differential equation with some unusual forcing functions. So for example, we're going to find the Laplace transform of what we call step functions. So for example, if we look at this one, we want to find the Laplace transform of a function that's defined as as 1 from 0 to 2, and then it becomes 0 once you get to 2. So here's the graph. So from 0 to 2, it's 1. The value of the function is 1. Then it becomes 0 after that. So just imagine solving a differential equation like we wanted to use undetermined coefficients or variation parameters, and we had a weird function like this. That wouldn't be helpful to us, those methods we've learned. So let's take a look at how to find the Laplace transform of a function like this, and then we can find solutions to problems that involve these sorts of functions. So we need to go back to the definition. I told you we could always use tables, but we might need to use the definition occasionally. So this is the type of problem, if I ever asked you to use the definition, it would be on something like this. So here's the definition of the Laplace transform of a function. So the interesting thing here, from 0 to 2, the function has the value of 1. From 2 to infinity, it has a value of 0. So we split the integral from 0 to infinity up into two integrals. So from 0 to 2, the value of the function is 1. So we leave the e to the minus st times 1 here, plus the integral from 2 to infinity, e to the minus st times 0. The value of the function is 0 from 2 to infinity. So what happens to this entire integral here? It's just 0 because you're multiplying by 0. Think of it as area under the curve. If the function's value is 0, there is no area under the curve. So this one is just 0. So we just need to evaluate this integral. So we're just left with e to the minus st. We're integrating with respect to t, so the s is like a constant. And it's just really a definite integral. It's just the integral from 0 to 2, so we don't have to do anything with any limits or anything. Antiderivative of e to the minus st is e to the minus st over negative s. Our limits are for t, because we're integrating with respect to t. My favorite thing to do is to pull the 1 over negative s out in front and not worry about it till the end. Plug in 2 for t and 0 for t. So we have e to the minus 2s minus e to the 0, because those are our limits of integration. Now e to the 0 is 1, so all we have in the parentheses is e to the minus 2s minus 1, and we're going to multiply by this negative, so it's really the same as 1 minus e to the minus 2s over s. So that's one thing you can start to notice when you have jump functions like this. You get these unusual, we haven't seen a Laplace transform that looks like this. We typically have these powers of s, like something over s squared plus k squared, or 1 over s minus a, 1 over s. We never have seen one like that. Let's take a look at another one. So this time we'll change it up just slightly. So what if from 0 to 2 it's 0, and then it becomes 1 once you reach 2 and beyond. So it's 0 from 0 to 2, and then it jumps up to 1 for all time after t equals 2. So here's our definition again. This time we're doing the same thing. So from 0 to 2, the value of the function is 0. So this time, this first integral is 0 because it's just the area. There is no area under that curve, right? And then from 2 to infinity, little f of t is 1. The value of the function is 1. So this time we have to evaluate an improper integral from 2 to infinity of e to the minus st dt. So again, this one is improper. So we replace the infinity, make it a definite integral, and take the limit as m approaches infinity. All right, here's our function, same antiderivative as before. We're taking the limit this time at limits of integration, or t equals 2 up to t equals m. plug in our limits of integration, plugging them in for t. So what happens here? We're taking this limit. Well, as long as s is positive, e to the minus s times m goes to 0. So this gives us 0. This doesn't depend on m. It's like a constant. So we just get 0 minus e to the minus 2s. Multiply by the, again, I factor out the minus 1 over s out in front. Multiply through, and you should get e to the minus s, e to the minus 2s over s. And again, notice that power of e. You get these unusual powers when you have a step function and you're finding the Laplace transform. So these are really the only problems that I'll have you use the definition to find the Laplace transform. All other ones will just be using the properties and the table of Laplace transforms.